today is I will start with Power ISA, and then I will go on vector processing. So there is a function that is available that you could use to support vector processing. So particularly, you want to multiply two matrices to come up with a third matrix. And then when we talk about matrix multiplication, then it comes in HPC, it comes in supercomputing, and then that problem is everywhere. And then if you want to solve something, or if you want to deal with some data, and then if you design a computer, for example, the processing code and everything, and then a supercomputer, then how do you measure whether that supercomputer outperforms the existing supercomputer, right? So for that time, you try to run some matrix multiplication. So there are if you look into the literature, there are benchmarks. So these benchmarks are matrix multiplication benchmarks. So particularly one benchmark is BLAST, so the library. So we'll talk about one construct that is in Power ISA that supports this vector processing and then tries to expedite the process of multiplying these matrices. After we talk about a little bit Power ISA, we'll go there. And then if we have more time, then I will go and talk about Power 10. So particularly, we'll talk about the summary of Power 10. What does the core architecture looks like? What are the features that are available there? And then what they are doing in the architecture itself so that the system can be used for SPC, this system can be used for supercomputing, this system can be used to crunch numbers, right? So if you want to crunch numbers and do a lot of calculations, then you have to worry about many different things. For example, the system should support some kind of computation, and then it has to expedite those computations, as well as they have to do the connection, the interconnection, the data transfer between two or more systems more efficient, right? So you need bandwidth, as well as you need that kind of support. So we'll talk about that. And then if we have time, then we'll go into a software implementation, microwatt, but we'll see how far we reach there. Otherwise, we'll continue from there. So as you see, we were here yesterday. Dr. Gutser, could you mute yourself, please? Yeah, perfect. So here, Power ISA, this is now open. So that means all the technology that is available there, the instruction set architecture, actually you can go and then, use that architecture, and then all the patents that are there with that architecture. So before the development, particularly the integrated circuit development or the chip manufacturing, was very limited to the manufacturing companies, and then it was not exposed to the other vendors who try to, let's suppose, come up with an embedded system or come up with some particular specific processor that will help them to do their job. Okay, so when this instructions and architecture is made open, then now it helps to have more research, more contribution, more development in this area, and then it is helping a lot. So the recent one is Power ISA 3.1. There is Open Power Foundation, OPF, and then you know that this lecture was also organized with association with Open Power Foundation. We'll talk about some of the features of Power ISA 3.1. So here, if you look into this one, August 2019, OpenISA announcement at North America Open Power Summit. So that happens every year. Then in February 13, 2020, there was final draft of the end user license. released by Open Power Foundation, and then April 2020, Power ISA 3 was contributed to Open Power Foundation, and then now Power ISA 3.1 was contributed to Open Power Foundation in May 2020. So here, Open Power ISA 3.1 is very similar to version 3. So 3.1 is a little bit extended, right? So there are compliance subsets. So we'll talk about them, what those compliance subsets are. So particularly to implement a processor, you have some set of instructions, okay? So they are fundamental to a processing chip. So basically the processing chip should support all the instructions. For example, if you give one instruction, let's suppose load, right? So you have load instruction, then the processor has to identify when you run that load instruction, what does it mean? So load means you have to load data from somewhere that is the source to somewhere that is the destination, right? So particularly load means we have some data in memory. So that's typically what happens. You have data in memory, and then you want to load that data to some register that is in processor, right? So the processor will just use the registers it has, and then if you have data in memory, it has to first copy in the register and then do the computation. So whether you need to always copy from memory to register and do the computation, or you can directly do the computation from memory, it depends on the architecture. For example, Power ISA architecture is load store architecture. So when you have load store architecture, then the processor cannot go to memory and then do the computation using the data that is there in memory. So you have to first copy the data that is there in memory to some register, and then only you will do the computation in register. And then the output is also going to be written in register, and then later that output is going to be written back to memory. So this is a load store architecture. So if you think about PowerPC or the Power ISA is load store architecture. But if you go into, for example, the architecture the other manufacturers use, there may be not load store, maybe memory related to. For example, you can directly go and access the memory and do the computation too. So there are different features. So here, what you can take away is that this architecture is load store, and then everything the processor computes, you have to copy first the data from memory to the registers and then do the computation. Okay, so you will see later how many registers that are available there, and then what is the size of each of the registers and everything. So it depends on the sizes of the registers too. So you have to worry about when you do the computation. For example, how a processor knows what kind of computation it needs to do for any command that you give. For example, you want to add two numbers, right? And then, so what is the standard format it uses to do that computation? For example, what is that register, one register, and then another register, and then where you are going to write output, and then how do you decode? For example, I have an instruction, it says that add R1, R2, R3. Let's suppose R1, R2, R3 are registers, and then add, right? So depending on the processor architecture and then the convention they use, whether you add R2 and R3 and put in R1, or you sum R1 and R2 and put in R3. So it depends on the architecture, and then they have the common format. That format tells, okay, if I write this instruction, then this instruction will read this these registers in certain order, and then the output is put in some register. And then if you know that convention, and you can write the program or write the assembly language code and everything in the way processor processes. Okay, so there are compliance subsets. So that means there might be huge number of instructions that are supported by power processor or power chip. And then we have compliance subsets, because since it is open, if you want to use this architecture and then build some processor chip, then And then if you want to verify that whether this is compliant with the specification that is provided by IBM, then they provide different classes, and then you can pick to implement certain class. If you pick to implement one class, then you have to implement all the instructions within that class, and then you can say that okay, and then you can ask IBM to see whether your implementation is compliant with the specification that is given by IBM. Okay, so we'll talk about this compliance subsets. There is custom extension space. Ambika was asking me yesterday, what is sandbox? So the sandbox is this. Okay, the definition of sandbox. What happens is that let's suppose you have a production system. Okay, so the production system, I mean, it doesn't matter. Let's suppose you have a banking system, right? And then let's suppose you apply for a credit card. And then in the banking system, if you apply online for a credit card, or you go to the bank and then apply for the card, then probably they will look at your credit score, they will look at your the different other history on the finance related, and then they will make a decision, right? So there is a decision system that is run by the, run by the bank. And then they have certain conditions. For example, whether you meet all these conditions, and then based on the conditions, then either they will approve, and then if they approve your card, then they will also set the limit. What is the credit limit that they assign to your card? And then so then assigning the limit, whether they approve you for a credit card or not, and everything. So there is a system that is going on. Okay, so every application, they will go through that system. So that's how they make decision, right? Now these banks are trying to see whether the decision method they use is right or not, right? So they have to change all the time. For example, if you look about US banking system, what happened is that after pandemic started, people were losing jobs. After they were losing jobs, they have to come up with a new decision system that will somehow lower the criteria, right? Lower the criteria for anyone to be approved for credit card or approved for loan or everything, right? So the people who do the risk analysis or the data modeling and everything, so they will test, they will use the data and then write code and everything and then test on site. So that test that you do will not affect the decision system that the bank is currently running. Okay, you are working on the side. So after you test through different methods using different data and everything, and then if you feel like this new method is giving better results, accommodating many, more than what this existing one accommodates, then after the testing and everything, then you can deploy that one to the main system, right? So the side work that you are doing there is kind of a sandbox. So we can call it a sandbox because you are working in the same environment, you are running things in the same environment and everything, but in the decision system, that is not playing the role until and unless you deploy as a main system. So you can work on the side so that you can test further in the system how things work and everything. So that is what the sandbox is. So this provides custom extension space for this architecture. So how does it work? Let's suppose you have a Power ISA, and then you have a processor, you are running Power ISA and everything. And then all the existing features that are supported by Power ISA, you can immediately use them. There is no problem. But let's suppose you want to somehow implement some new feature in Power ISA. What do? You work it as a custom extension space or the sandbox, and then so that when you are running that and then when you run that, it will not affect it. It is not the main part of the system. You are working on the side, and then if you want to make it as a main part of the system, then you have to later deploy that into the main system. So it becomes becomes one of the feature. So that is sandbox. You work on the side. For example, sometime for some projects you work in GitHub, and then let's suppose there is a main part of the code. You clone the GitHub directory, and then you work on your own, and then you come up with a new feature on something, and then so when you clone that that GitHub directory, and then you implement the new feature and everything, it doesn't directly goes to the main GitHub directory that is there and then everyone is using, right? When you have enough tests and everything, and then everyone approved that this new feature should be the part of the main system, then when you commit, then it goes and reflected into the main directory, right? So the side directory that you work can be called as a sandbox. Ambika, do you think you found your answer? This is for others too. You know, if you have any doubt on anything, you can simply ask me. Do not wait until the end of the lecture, because there are so many new terms that we're going to use here, because there is, you know, this is the whole different landscape. So we are going to use some very new terms and everything, and then you know, you can just ask me. All right. So this is the Power ISA timeline. So if you look here, so the current architecture is Power 10. Okay, so Power ISA 3.1 is implemented in Power 10 processors. Okay, so if you look here, the Power 10. So there are, so since we are talking about Power 10, there are previous, you know, 9 versions: P1, Power, you know, Power Processor 1, Power Processor 2, Power Processor 3, 4, 5, 6, 7, 8, 9, and then recent is 10. So if you look here, so this you know, this development has happened in 30 years time. Okay, they are constantly improving their instruction set architecture and then making better. For example, what are the supports, what are the features that you add? So if you look into Power Processor, previous Power Processor, and then this Power Processor, or the previous version of ISA and then this new version, so more features are added, more instructions are added, so that you could do more and more. For example, one feature is cryptocurrency, right? So for the cryptocurrency, you have to crunch big amount of numbers, and then you are running hash functions and everything. And then probably in ISA 3.1 Power 10, they are also providing a feature where you could do those kind of you know, features. Okay, I will talk about those ones too, just in a second. So if you look here, you have IBM server, so around 1999 Power, and then you have Power PC embedded. So for the embedded computing, we have here, and then there are different ones. For example, if you look initial development, then if you want to talk about embedded systems which have energy constraints and everything, then you have some kind of a different kind of instruction sets that were there, you know, not combined, not unified. Okay. And then in around 2006, when there is a Power ISA 2.03, then these embedded features were also included there. And then you can see that they were combined and then more unified. Okay. And then in 2017 around, you have Power ISA 3, and then now in the open Power ISA, you have all custom extensions. For example, sandboxing feature is available there. Power, you know, ISA 3 is there, and then so this whole combination is more giving you the you know, big you know, instruction set architecture that is more applicable to different scenarios. So embedded features. So these embedded features are, let's suppose you have some kind of a smart device. Let's suppose you have a smart device. It has just some functionalities, not many you know, arbitrary functionalities, some functionalities. For example, you want to send, let's suppose one feature would be, let's suppose you have a sensor that senses temperature. Okay, so you have a sensor that senses temperature, you are putting somewhere, there is a location, and then in the communication and then the data sensing, then you can specify, okay, this particular sensor is going to sense temperature in 15 minutes interval. Okay, so you have a frequency, so 15 minutes interval, right? After it senses data, then it has to make a decision. The decision is that if you sense temperature after 15 minutes. And then let's suppose your previous temperature that was taken 15 minutes ago, and then the now, let's suppose, doesn't change. Okay, so let's suppose 24 degrees. Okay, so one. And then, so after you sense the temperature, the goal is to send the data to some processing, central command or control, so that you could make a decision. For example, if you look at the heating system inside the house, then what happens is that the thermostat is working on, let's suppose if you are heating the house, it's winter and heating the house, then what happens is that there are sensors, and then the thermostat is working. Thermostat is correlated with the sensor that is sensing the temperature. So thermostat will set, let's suppose you say that, okay, I want to set in 25, and then sensor is sensing 24. At that time, the thermostat is going to work on, heating the house. Okay, so it is constantly heating. So let's suppose 15 minutes before and 15 minutes after, the sensor is sensing 24. So let's suppose the data that you sensed 15 minutes ago, you sent to the thermostat. Okay, after 15 minutes too, you are sensing 24. So at that time, you can make a decision on whether you want to send that data to the thermostat or not. The new data that you sensed is not giving new information to thermostat, because 24 means thermostat still has to work. So the information that you provide is not going to give you new new information to thermostat. 25 would be nice, because if the temperature is 25, thermostat could stop at that time because the temperature is now 25, the set temperature, right? So the embedded features are such kind of features where some processor that you design that works in a limited scenario for certain application, just one application, at that time you could customize, you can make some instructions, some instructions cover just certain part that is relevant to the particular application where you are running that system. You don't need to cover everything. So these are typically called embedded features. For example, whether I want to, whether I want to do the computation or not. For example, I have an add function. In the add function, I have registers R1, R2, R3, and then whether I use R1, R2, and then use R3, or I will just see, I'm not going to use 3 different registers. Probably I will use, let's suppose, 2 registers. What I do is that R1 and R3, let's suppose you give 2 registers, and then R1 and R3 data, you take it, sum it, and put in R1. Okay, so that kind of, the embedded features are more specific to some application, so it will help to somehow make a system a little bit more constrained, so that you do not need too much computation power, you do not need too much memory, you do not need too many number of registers and everything, so that you could still do the computation that is related to particular applications. So embedded systems are designed particularly focusing on some application that you want to solve using processors. So for example, if you want to use full custom instruction set architecture to do that, maybe it is computation heavy, and then it will need more power. So you have to worry about the battery power, and then worry about different constants it has. So so these are embedded features. So these features are more restricted, and then particular to some applications that you could design. So the prefix, I will talk about the prefix when we go in later slides. Okay, so there is a prefix notion on IBM Power ISA 3.1. So that helps to make the instruction set architecture that is used by Power IBM more flexible in different scenarios. You can actually program in a different way depending on the need. Okay, so Power architecture format, there are, so the specification, so if you look into Power ISA specification, there is a big document. So that document is around 1,600 pages. Okay, so this 1,600 pages document, what it does is that, okay, what is there in the instruction set architecture? how the power architecture works. So how do you input data? How do you process data? For example, how do you run branch instructions? How do you run sum? For example, you have add instruction, right? How do you execute that? How do you read registers? So for example, you have 32-bit registers. Then if you have 32-bit registers, then you have to worry on how do you read data that you have in 32-bit registers. So for example, in 32-bit registers, let's suppose we are putting the value 10 in one register, right? When you put value 10, so the binary equivalent of 10 will be 1010, right? So that would be 10. And then there are 32 bits, and then 1010, maybe you will put in the last significant, last 4 bits, 1010, and then there are other bits, right? Other 28 bits. What are you going to put there in those 28 bits? So that has to be specified in the architecture itself. Okay, so so that way, when you know that convention, then it is easy for you to process, right? Because eventually, when you go and then try to decode the instruction, then when you decode the instruction, you have to go and then, let's suppose, add R1, R2, R3. This R1, R2, R3 are the registers, and then you have add. So this add is the construct that tells the processor what to do. And then we are writing add just for our convention, but it has some specific number that is associated with it. We call it opcode, right? So that number tells, for example, number 81 or some bit there, it tells that, okay, this is add. So this kind of information you have to you have to be exactly the same as defined in the architecture, so that you could write better. So we have 3 books, particularly 3 books. So why they divided into 3 books? So it helps to somehow identify what are the basic instructions, and then you go a little bit more into a storage model, and then you have other, for example, when you have exceptions, how do you manage memory? How do you debug some special control and resources? So, so there are 3 books. So book 1 is very basic. What it does is that it defines user instruction set architecture. So, for example, how do you reference memory? Okay. How do you control the flow? For example, you have branch instructions, right? How do you execute a branch instruction? If the branch instruction comes, what do you do, right? So let's suppose you have a branch instruction, you identify that that instruction is a branch instruction. Now you have to, when you identify, then you have to go to the place where that branch instruction tells you to execute the next instruction, right? So for that one, think about it, you have to put that information. So branch target address you have to put. The target address tells that, okay, this is the instruction that is there, and then I have to run this instruction going from there. Now, when you know that that is the target address, you have to load the instruction that is instructed in branch instruction, right? So the branch, when you run the branch instruction, it will take you somewhere. There is a program counter, and then this program counter will tell, okay, I'm running this instruction, and then you have to go read this instruction, and then you have to, fetch that instruction to the processor and then decode it. Decoding tells that what this instruction ask you to do, and then do the necessary operation, right? So kind of flow control. And then you are, whether you are dealing with integer data or you are dealing with floating point data. And then so the integer data is stored in certain way, floating point data is stored in certain way. You have to know the convention. For example, how do you store floating point data? And then you have also numeric acceleration. So can you expedite the process of computing these numeric results? So this is covered in book 1. So this is more into application level programming model, and then it covers basic instructions that are there. Now you can go into book 2. So this is inside the same document. So as I mentioned, it's more than 500 pages document. No, 1500 pages document. And then the book second talk about the virtual environment architecture. So particularly, you go into thread and then the resource interaction. So basically, you talk about how do you do the time synchronization, how do you do resource synchronization, how do you manage cache? Because when you talk about running different threads, then you have to worry about running a cache coherence protocol that makes sure that the data that is accessed by two or more threads and processors is coherent all the time. So the cache coherence is a major problem when you talk about multi-core computing sharing same shared memory. Okay, similarly, storage features that is covered in book second. So the more library level programming model, and then so this is in addition to the basic instruction set architecture that happens for somehow sequential processing. So here we can say going from sequential execution with basic instructions to going into more multi-core thread level programming, and then what are the features that are available there, what are the instructions, and then what you could do, how do you create thread, when you create thread, what you need to create inside the architecture so that you could deal with that thread, you could run necessary functions within that thread and everything. And then, so the book third is about supervisor instructions. For example, again, it comes with memory management. So you go into manage memory. How do you, uh, get data from memory? How do you store it in memory? All that. So you have to, you also have debug facilities. So how do you, debug anything that happens, and exceptions, interrupts, and everything. So here, this is more supervisor, hypervisor kind of programming model that is there. So it also supports some operating environment architecture. So you have to go from operating system level to the hardware level. So you need to somehow make a bridge between what operating system dictates you to do, and then you go, and then how the architecture works. So there is a there is a mapping you have to do, and then it somehow goes in higher level, and then so it gives exceptions, interrupts, and everything, and then translate them into the way the hardware understands. So compliancy, if you look into compliancy, for example, any design that you make or that you build based on this open power ISA architecture, and then the open power ISA computation model, then you have to support the base architecture. Okay, so this base architecture is never optional. Okay, so any system that you design using open power ISA, it has to support this base architecture. It is never optional. Okay, and so this base architecture, any any design that you build, so it has to support that. And then you can support at least one of the compliance subsets. Now you can pick one of the compliance subset here. For example, the one subset is ACS. This is auxiliary instructions compliance subset. LCS, Linux compliance subset. SFFS, that is scalar fixed point plus floating point compliance subset. SFS, scalar fixed point compliance subset. And then you have optional features as well. So I will show you in a diagram in the next slide where they belong, and then what is the hierarchy of these subsets. And then also we will see how many instructions that are there in every subset. Okay, and then may support any optional features for the compliance subset. Okay, so if you try to support any optional feature, then you have to support all the optional features in the design that you built to be compliant. So if you don't want to be compliant, that's fine. But if you want to be compliant with the open power ISA specification given, then you have to support the whole base architecture plus at least one of the subset that defined per compliancy. And then you can support custom extensions, not just the optional features. There are more custom extensions. So as we talked about architecture sandbox, so this architecture sandbox gives you an option to try new instructions. So basically you can work on some instructions, and then if these instructions work well, they do not conflict with any of the instructions that are there, and then you test enough, and then everyone agrees that this feature is a new feature that is supported in the system, then this custom extension can be the part of the main architecture. And then if there are, let's suppose, 1400 instructions, and then if you design a custom extension instruction, and then that is validated to be part of the instruction set architecture, then there would be 1401 number of instructions that are supported in Open Power ISA. Okay, so this gives room for developers to come up with new ideas, and then not just inside IBM. So this custom extension can be proposed by the developers outside IBM too. For example, we came up with this feature. So this feature, we tested. These are the results, and then and then we would like it to be included in the Open Power ISA architecture there, and then that can be part of the main one. So that's how the development is. And if you look into previous versions of ISA and then the new, there are more and more functionalities that are added on top of making hardware efficient. So you need hardware support to run these instructions, whatever instructions that you come up with. And then but if you come up with the efficient hardware that supports, but the instruction is not there, then you are not utilizing the the enough functionality that are given by the architecture itself. So this is a two-way process. So innovation in one area depends on innovation on other two, and then they have to go side by side. So and then it also may utilize a combination of hardware and firmware. Any firmware must rely on base architecture, and then the included optional features and the included custom extensions must honor restrictions specified in the architecture for use of storage, and must honor explicitly prohibited uses. So any firmware that you design, it has to support base architecture, and then so you can have optional features as well. And then the firmware, if that is designed, it has to honor some of the restrictions that are imposed. For example, these restrictions are imposed keeping in mind somehow consistent development, and then try to see at least this particular design supports these features or includes these features, and then it will be easy to see classify these new designs. So so this is how it goes. Here, this is the compliance subset. So if you look into full version 3.1 ISA, then it has 1419 instructions. Okay. So this is the full architecture compliance. If you look here on the bottom, this is the full architecture compliance. And then if any architecture that is compliant is full architecture of whatever offered by Power ISA 3.1, then it will have 1419 instructions. Okay. And then you can from the version 3.1, you can minus, so you can remove always optional features. You can also remove deprecated features. So if you remove those features, and then whatever design that you come up with is the ACS, it has 1099 instructions. So basically 1099 means 320 instructions are gone. So if you remove these 320 instructions that are related to optional features and deprecated features, then you will have this subset. Okay. Now from that subset, let's suppose you remove these Linux optional features. Okay. If you remove Linux optional features, then you will come into so there are in Linux subset there are 962 instructions. So from the ACS, you remove some of the instructions, and then you come into Linux subset. From Linux subset, you remove some Linux optional features, and then you come into you have this SFFS subset. So scalar, fixed point, and floating point subset. And then from there, when you remove SFFS features, then you will come into SFS, that is scalar fixed point subset. So any of the 4 subsets can be chosen per compliance, so pick any of the 4 subsets, and then you can make a design that is compliant with the specification that is provided by OpenPower ISA. So you can go from the so the top smaller one, the green one, and then you can go to yellow one, you can go to red one, you can go to blue one, and then if you go further, then you will have the full architecture. That's how the compliance subset works for this one. So here, compliance subset, if you look here, so the base architecture, you will have 129 instructions. And then if you go into combination of scalar fixed point plus floating point subset, then you will have total 214 instructions. If you go to Linux subset, so so scalar fixed point, I think it's just a computation related. I think it's for example, you have a some instructions that can just deal with integers. Okay, so some scalar values, integers, and then some deal with not scalar values, other values. So when you deal with that, so for example, if you know that you are not dealing with any floating point instructions, then you can have constraints. You can have simplification on the let's suppose whether you want to do 32-bit registers or 64-bit registers, or how do you store data. So it somehow simplifies. So particularly scalar has not that much of a meaning here, but I will suggest you to go look into the Power ISA specification, the whole document, if you want to dive further into this one. Okay, so actually there is a lot of content there for every instruction. If we want to talk about how these instructions are written and then how they will be stored in registers, and then how how a processor identifies or how the processor decodes that, oh, this is what this instruction asks me to do, then there is a lot of this decoding happening, and then definitely I would suggest you to go there and then look at it. Okay, and then you have a Linux subset. So it adds many more instructions. So from 214 you go to 962. Then you have ACS. It adds more. For example, here you see some of the big Indian way of putting data, event-based branch. So that is the new feature. So some event happens. So for example, let's suppose you are using this processor architecture to do event-based computing, and then so how do you deal with, okay, if this event happens, then you take this branch. If this event happens, take that branch. So it has to be supported like that. Load store strings, so that is supported there. Load store multiple decimal float, quad precision float. So for some of the computations, you need more precision than that is given by floating point representation. So at that time, you want to go into the double precision and then how to deal with that. So always optional features. So it has 320 instructions. So these always optional features are also added in the full compliant architecture. For example, power management. Power management is not necessary, like the mandatory feature. For example, data stream preface is not the mandatory feature. Matrix, so Matrix Math Assist MMA, we are going to talk about it today a little bit. So that is also optional feature. So for example, for high performance computing or supercomputing where you want to crunch numbers, maybe if you use this construct, it will help you to expedite the process, but this is not coming in the main architecture. So in the subset it's not there, but if you want to have the full version, then you can have that. So today I will talk about Matrix Math Assist a little bit in a while. So what does that construct provide, and then how could you expedite the process when you try to multiply matrices? So, and then you have architecture sandbox. So this architecture sandbox is for customization with limited applicability. So for example, here you can go and then work on designing new instruction here. And then if this instruction is verified, and then, okay, this instruction is working correctly, and then there is no conflict and everything. So after the verification, these new instructions that are developed here can be part of optional features. And then some of the optional features might go into become part of the subsets, depending on the need, depending on the support from the architecture and everything. So this is how the development happens. And then here in the architecture sandbox area, they always try to develop these new instructions and then come up with the support from the architecture itself, and then it has to provide some new feature. Then that is provided by the existing instructions. So, so the compliance subset permits custom extensions. Okay. So the architecture sandbox features are intended to allow implementation-dependent customization. For facilities with broad applicability, developers are strongly encouraged to submit a proposal for adoption into the architecture. So let's suppose you are a developer, you came up with a new feature, new instruction, then you can actually submit a proposal about this new instruction to be adopted into the architecture. And then so they will review that particular proposal on a new feature, new extension, and then they will look into the test data, they verify everything, and then it is not conflicting, everything fine, and then they could actually put in the architecture. So adopted proposals, if the proposal is accepted, will become optional or required feature of the architecture. For example, some of the feature that is not already there, that feature is so useful, it has to be part of the base architecture. You can go and make it the part of the base architecture. Okay, if that feature is useful, but if they think that this doesn't need to be a part of the required feature, then it can be part of optional feature as well. So these will be assigned resources that are not in the architecture sandbox to avoid fragmentation of the architecture. So if you do not support this custom extensions, then there is a problem on, let's suppose you have an architecture, and then there is a new development happening on from the developer side and others, and then if these new extensions are not included in the architecture, then you might say, oh, this is the custom version of the architecture we develop based on these new instructions that we are developing. So there is a issue of fragmentation in the architecture. That means it can it can grow in different ways. For example, one of that is Linux. If you are familiar with Linux, then we have so many different versions of Linux and everything, and there is a core architecture, and then everyone is developing new features and adding new features based on their need, and then that's why we have Ubuntu, we have Red Hat, we have different versions. Okay. Facilities described in proposals that are not adopted into the architecture may be implemented as custom extensions using the architecture sandbox. Okay, so that feature is also there too. So they try to accommodate all the new development in this area. So if you have a custom extension, then the system software and tools and support may not be guaranteed. because for custom extensions, they do not give that much focus on whether there is appropriate software and tools and support for any of the instruction that is available. Developers are encouraged to provide a means to disable custom extensions to prevent an architecture that is supported by standard system software and tools in. So these custom extensions you can put, and then let's suppose that becomes part of the architecture. And then let's suppose you put in the additional optional feature, and then these optional features, although added, there is an option to disable or enable that feature. For example, in Power 9, I will tell you one feature. So there is a new notion of transactional memory. So this transactional memory, what it does is it tries not to lock the data. So what is the common notion? Common notion is if you are using some data, you are sharing that data, then you want to make sure that when you use that data, no one else goes and uses that data, right? It's a critical section. Maybe that term you are familiar. So the critical section can be accessed by one thread or one processor at a time. And then after you are done working, then another processor comes and does, right? So this critical section access using locks is a little bit limiting, because think about a big distributed system where you are running jobs, and then what is the chance that two or more processors at the same time they come to access the same location, right? So you try to use you try not to use lock, and then let those processors go and access the data. And then later, when you figure out that actually there is a conflict, that means two or more access the data at the same time, then you deal with it later. Okay, so that feature is called transactional memory. Very basic. There is a huge development in this area too, but very basic, that is the feature. And then in Power 9, that feature was included. Okay, so that feature was included, but included is a optional feature. So this optional feature, if you want to use it, then there is a way to activate that feature. You enable that feature in the architecture. If you do not want to use that feature, then you have the option to disable that feature. So that has to be given. So this helps. For example, these custom extensions, there is a way to disable the custom extension if that is not needed or you do not want to use it. If you want to use it, you can go and then enable that feature and then do experimentation with that. For example, people who are doing research, they might want to use those features to see how efficiently that feature is working, or so at that time they could go and then enable that feature and then work on that. But for general users, and then they are not using that feature, there's a way to disable too, because some of these features, if you are not careful, then they might conflict with something that you do on the normal other side. Okay, so you want to make sure that it is not providing any overhead or not conflicting with something that you do. So foundation for expansion, because there is 3.1 includes a number of new features. So you have to go to the document to see the depth of these new features, but you have so many. For example, persistent storage sync feature, because think about, there is a development on persistent storage as non-volatile memory and everything, and then the architecture itself has to support that, and then so they have persistent storage sync feature added there. For example, metrics math assist. So this is we are going to see in a bit. We'll talk about that. What does it mean? Copy paste extensions. You have pause and wait reserve. So these all features are related to some of the computation that you do, and then when these features are there, then the architecture itself is more applicable to variety of systems. So there is a prefix architecture. So it adopts this architecture. So if you look into this one, So here you have, so this is more into making it flexible for different kind of implementations. So we have 32-bit suffix. So this is how it is organized, okay? In the, okay, persistent storage is this. So persistent storage is, let's suppose you have a RAM, okay? So we have a volatile RAM, okay? So when in the memory hierarchy, what happens is that you have processor has some registers, and then it has L1 cache, it has L2 cache, or depending on, you might have different levels of cache, and then you have memory. So this like a RAM or main level memory or shared memory that we call it. So when we talk about memory, we do not talk about the secondary storage, for example, hard disks or all that, right? So cache is volatile. You know that the cache is volatile, but it's faster than the main memory. And then main memory is RAM or DRAM, or that's what you see. So the RAM is also volatile. Okay, volatile. Now the new way is that you replace RAM that is volatile with that RAM is non-volatile. So that means somehow this what it does is that this bridges the gap between the secondary storage. Secondary storage is always non-volatile. If you store that there in hard disks, it will be there, right? And then the cache is volatile. So what you do is that if you make the main memory non-volatile or persistent, then you might not need secondary storage as well. You know, in the computation, it is not needed. Okay, so so that is what the non-volatile memory is. You know, so when you have non-volatile memory, then the intermediate computation, what you do, uh, everything has to be stored in the memory. When you store in memory, let's suppose you store something in memory. If you store something in memory, then it is persistent there, right? And then if the computation is no, this is the traditional volatile memory architecture, which has RAM, which have cache and then RAM and then the secondary storage. You know, there is another fundamental limitation comes into picture, where if you want to access the main memory, then it has to be faster access, right? So if you have a big big memory, then there is a problem of faster accessing and everything. So there is a whole different story there. Okay, so what I say is that there is a design decision on, right? So design decision on why the memory was volatile, and then why there was not big memory and everything that was there. Now with the new development, what is happening is that you can access memory faster. You can do some, there are other different contexts going on. So if you have the non-volatile memory, then how do you support? Let's suppose the non-volatile memory is there. Okay, so we replace the volatile memory with non-volatile memory. Okay, let's not go into the discussion on that. Then how do you support computation there? Okay, if the processors do not crash or there is no problem and everything, then whatever you write, the intermediate computation that you write there and everything, later you can see, okay, this is the output, and this is the intermediate computation, and then you can remove that computation, erase from the persistent memory and all that. But if there is an intermediate computation, and then let's suppose the computation is not finished, then you don't know whether that is the value that you want to use, store there forever, or you have to remove that. Okay, so it's a log. So you have to store a log. The log is the intermediate computation that you did there, and then the log has to become the main part after the computation finished successfully, right? So after you commit the data and everything. So to identify that, there is a challenge. And then so that's why if you look into the persistent memory research, then in the persistent memory research, they try to see how to optimize that process, how to make it better and all that. So Ambika, you asked very interesting question on persistent storage, but there is a lot going on. This is a new topic. There is huge research going on, and then maybe you would like to know further. If you go read some paper in persistent storage, you will get to know what I'm talking about. Or we can talk offline if you want to know more. So this prefix architecture, so what it does is, depending on the need, it makes it more flexible. For example, we have two forms. For example, this suffix and prefix, we have 64-bit. So if you look into the suffix, then it's 32-bit. If you look into the prefix, it's 32-bit. So you can actually, this prefix architecture gives you flexibility on how do you interpret the register. Okay, so how do you interpret what the architecture means for this instruction? For example, if you want to use prefix architecture, then PO, the primary opcode, you have to put the bit 1. If you put the bit 1, then it says that, okay, oh, I'm using the prefix architecture. If you put PO 0, then it just says that it's 8-byte opcode, and then you are not using prefix architecture. Okay, so it gives more more flexibility on many different features. For example, matrix multiply assist, that new feature. If you have the specific architecture, then it supports that feature too. So so somehow this prefix architecture helps you to give a generous room for expanded capabilities, including opcode space and then additional modifiers, so that you could go and then make this architecture more useful for different contexts. So there is one example on, for example, the opcode map. How do you map, and then the opcode space and everything here. So I will not go and then try to discuss more this one. So if you look into this figure, this is also in that document. You can go and then read that. And then, of course, we can talk in offline more in detail if you want about the specifics of this prefix architecture. With this, what I want to do is that I want to take a 5 minutes break here. So you will get a little bit break and then come back. I will also take a break and come back. So it's 9:35 here. Let's meet at 9:40. My 9:40 means your 8:10, I guess.
Yeah. So
Uh,
we take a break for 5 minutes. Yes, sure.
Yeah. And then in the meantime, if you have any question related to the Power ISA compliance and introduction, you can write in chat box, or you can ask me offline, or after we come back at 8:10. And then I will talk particularly about metrics and multiply assist instruction, and then how does it help in the high performance computing. Okay.
Yeah, sure.
So see you in 5 minutes.
Yeah, please.
All right. Welcome again. So,
Yeah, please continue.
yeah, let's talk about one feature. So, I know this is a very advanced feature, but you might need to, you might like it to know. Uh, it's a very interesting feature. As you see that this is related to matrix multiplication. Okay, so as I mentioned before, this is a very difficult problem. Still, people work on new ideas to matrix multiplication faster than before in different contexts. And then this is also related to the benchmarking new supercomputer different national labs and different countries design. So you have benchmarks. So there's benchmarks particular to matrix multiplication. They run in these new architectures and then try to see how good that architecture is. So it has to beat the record that is given in the existing architecture to know that that new supercomputer is better than the existing ones, right? So here, if you talk about high performance computing, IBM is IBM is in the forefront of the supercomputers. For example, IBM Blue Gene, if you look into that, IBM has many variations of Blue Gene, and then even the different universities and different national labs, when they design these new supercomputers, they use as building block the power architecture as well. So these things are there. So what is the technical detail that goes inside, right? So it's about three things. So you have to crunch numbers, okay? So what does it mean by crunching numbers? So you perform as many arithmetic operations as possible. So the goal is, if you could do many arithmetic operations, per unit time, then that means your system is better. Let's suppose you have a system that does 1,000 arithmetic operations per second, and then you go increase into 1,200, increase into 1,500, increase 2 times, 4 times, 8 times, right? So that is number crunching. So that is required, because if you want to do computation faster, you have to do this, do these operations faster, many of them, okay? And then you have memory bandwidth. So, okay, processor might be ready to do the computation, but the data has to be available to the processor. If the data is not available to processor, then the processor cannot really do the computation. It has to wait for the data to be available, right? So that is the whole story behind it. So as Dr. Guzzer mentioned before, so we have processor speed. Okay, so the processor speed, if you see the chart, processor speeds are somehow growing linearly, were growing linearly when there was advancement in sequential computation. Now they are going a little bit flat because of the multi-core architectures, but somehow their speed rate is very high. If you look at memory, then the memory speed is also going high, but there is a huge gap. If you start from 1980 around and then you come towards recent times, then the gap is increasing, right? So when that gap is increasing, so that's why we use cache. So what is the motivation behind designing a cache? Because cache somehow bridges the gap, this speed gap between processor and memory, so that somehow you try to expedite the process of computation from processor. So memory bandwidth is also very related, so that you read and write as much data from to memory as possible. Okay, you have to. If you could write and read more data from memory per unit time, then there is a chance that you can run many arithmetic operations per unit time. Okay, so if you look into the process from the processor side, processors remain idle, like more time, because they are always waiting for data to come from memory to the processor so that they could execute. And then if you think about Power ISA. Power ISA is load store architecture. So everything has to be loaded to the registers for the computation. And then for everything to be loaded to the registers, data has to come from memory to the registers and then go to the memory. So read and write is quite often. And then you want to do much data read and write from memory. For that one, you have to be able to write many blocks of data back, from and to memory. So that's the memory bandwidth. So you need more bandwidth. And then we have interconnect. So let's suppose if you are talking about supercomputer, then one computing node is there, another computing node is somewhere, and then you are connecting these computing nodes and then somehow making a big system of, let's suppose, 1,000 computing nodes and all that, right? So when you have 1,000 computing nodes, think about a Power 10 processor. So Power 10 processor is going to be either one node, one computing node, or part of one computing node. Let's suppose we put 4 power processors together and make it as a computing node. And then we have 1,000 of them. And then you are connecting in certain way, right? When you connect in certain way, then what is the goal? The goal is communicate between elements as fast as possible, right? So the data might be in another computing node, and then you are trying to get that data to your node to do the computation. So you have the notion of local node and then the remote node. And then if the data is in local node, then it is very fast. But the data is in remote node, then you have to go and get that data. And then you want to get that data as fast as possible. So when you have this combination, you have a processing, you can process many instructions per unit time. You can read and write from memory many blocks per unit time. And then you can send data between the 2 computing nodes within a processor, within a supercomputer, or if you have just the Power 10 processor within the processors within that computing node faster, then the whole combination will give you the give you the necessary background for supercomputing. Okay. So particularly today, we're going to talk about what are the number crunching features that are available there, and then the matrix multiply assist feature provides. And for the interconnect, when I talk about Power 10 architecture, so I'm going to talk about Power 10 architecture next. If we have time today, we will talk about that. Otherwise, we'll talk tomorrow. And then when I talk about the architecture tomorrow, you will see how they have taken care of doing this interconnect as fast as possible. There are certain ways of clustering the memory, certain ways of communicating between memory and everything. So there is a fundamental limitation on these interconnection topologies that you use. For example, zip interconnection networks that you use, for example, grid mesh or other topologies. So you want to reach to the fundamental limit of that topology. For example, if you look into the topology itself, the topology provides lower bound on, okay, you need at least this much latency, you need at least this much, this much processing to be able to, transfer data or communicate data, right? So you want to hit that minimum, and then you want to pick the topology that is best depending on the latency, depending on different parameters. You know, how many interconnections that you try to do, and then whether that interconnection network is easy to write in the integrated circuit or not, because you have to make it the VLSI design and everything. So there are pros and cons on those ones. So you want to hit the fundamental limit on that, provided by the topology itself, and then try to move data. Okay. So in the open power, IBM is providing some of these technologies open, so that we could use in SBC. Okay. So here we'll talk about number crunching and memory bandwidth. So today, whatever feature the matrix multiply assist feature we talk about, it tries to address 2 issues here: the number crunching issues, and then the memory bandwidth issues. Okay. So interconnect issue is not discussed here, but when I talk about Power 10, you will get to know how it is taken into account on how to communicate between elements as fast as possible. So Ambika is asking, what is contributing to increase in memory speed? So, for example, the contributing factors in the memory speed increase is, for example, when you go and read the data from memory, instead of reading one block, if you have a feature to read many blocks. Another feature would be, let's suppose, the prefetching, that you somehow have a microarchitecture written. That microarchitecture tries to predict what processor is going to use next, what processor is going to ask next in terms of memory data, and then predict on that. And then even before processor asks you for that data, you go to memory and then paste that data back to the cache. That will help too. So I think I did not say memory speed is increasing. Actually, memory speed is increasing, but it's increasing slowly compared to the processors. So there is a trade-off on cost and then the memory bandwidth. So that is the convention that is used in the memory design. So you can have a very high speed memory, but there is a trade-off on the speed and then the cost. So the convention is that you will increase the memory bandwidth, not very proportional to the processor speed. Okay, so this is another area, Ambika. If I talk about this, we'll go into completely different territory. I can talk about that, but maybe offline. We can talk about it. This is a very
Yes,
interesting
Professor, you go as per
issue.
your schedule, please.
Yeah,
Yeah.
but I
I'll address her
love to.
point later on offline. Yeah.
Okay, and then I can help that too. But this is a very interesting question that you asked. Actually, there is the main answer lies.
True.
Okay, and then so interconnect. When I talk about Power 10, then we'll get to know what are they doing on making this interconnect as fast as possible. So I'll skip this. Let's go into the details of matrix multiply assist MMA. So it leads to very efficient implementations for SPC. Okay, and then so these are the kind of registers that are available. So you have 64 vector scalar registers here, VSR, that you see from 0 up to 63, and then the size of them is 128 bits. Okay. And then so here you have this VSR registers 0 up to 60. So you have 64 of those registers of size 128 bits. And then within that space, so this is the the vector scalar register space, right? And then within that, you have floating point registers too. There are actually 32 floating point registers you see, and then these registers are of 32 bits. Okay. So just keep this in mind. So if you represent the floating point register, then it takes the half area of a vector scalar register. Okay, so there are 64 of them. Floating point, there are 32 of them. Okay, now we have the notion of accumulator. Okay, that is defined in bar ISA. So the accumulators, what accumulators are? They are 4x4 array. So these are two-dimensional array. As you see here, accumulator A is like this one, A00, A01, so on. So each element is of 32-bit, okay? 32-bit, and then actually you can make extension to 64-bit as well. So this accumulator, if it has 32-bit, then it is 4x4 array. And then if you want to make 64-bit extension, I can tell you this array becomes 4 times 2, right? Because each element is of 32-bit here, so that's why you can accommodate 4 elements in a row. That if I have 64-bit element, then I can just accommodate 2 elements. Okay, so that is a very simple extension to go to 64-bit. They may not do that. Okay, we'll see. But anyway, this is how it works. These elements can be either 32-bit signed integers, so we write as integer 32 int 32, or 32-bit single precision floating points. So if that is the single precision floating point numbers, then FP32. So let me not go into single, what is the single precision and then all that, okay? So integer 32, floating point 32. This is how it works. Each accumulator is a software managed shadow to a set of 4 consecutive BSRs, okay? So here I was talking about this BSRs. So here this accumulator is written in this the vector scalar registers. So in the vector scalar registers, think about how can you write that particular this accumulator there. So you can use 4 consecutive BSRs. So when you use 4 consecutive BSRs, then what happens? Think about one row. One row is becoming 128 bit, right? So in this accumulator, so 128 bit. And then if you use 4 BSRs, this 4 BSR, one BSR is of 128 bit. There are 4 of such rows of 128 bit. And then you can use these 4 BSR registers to represent this accumulator. Okay, so so you have in Power 10 eight of the architect, so 8 of the accumulators that are written in this architecture. Why 8? So you see that here the first half of the registers here, there's a vector scalar registers. There's the inside it the floating point too. So if you want to have the accumulator written here, you have only 32-bit registers that are left with 128-bit space. So in 32, one accumulator needs 4 rows or 4 of these the vector scalar registers. Then in 32 registers, I can only accommodate 8 accumulators. Okay, that's what it is. And then you can state. So you can actually explicitly transfer between accumulators and BSRs using this function. So when you write an accumulator, then you are using these 4 BSR registers and then putting the information. Then you will say that, okay, oh, now I'm treating that as an accumulator. I'm now treating that particular register as a vector register using this function. For example, from the BSX move from accelerator, okay, BSX move to accelerator. So from the vector scalar register, you want to move to the accumulator. Now saying that this particular register is now put in the accumulator, or from the accumulator you want to the register. So you can have this translation using this function, XXMFACC. So from accumulator to accumulator. Okay, so you have this the instructions available. Now we have outer product. So let's suppose you have you have the outer product definition. It will come later. So I will talk about outer product one. But you have this outer product instruction. What happens is that accumulators are updated by rank k update instructions. How do you update? The input would be 1 accumulator and then 2 BSRs, X and Y. Okay. And then the output will be 1 accumulator. So that's how it works. So you give 1 accumulator and then 2 vector scalar registers, and then you have 2 matrices X, Y. And then when you do the computation, you will have 1 accumulator output. I will show you what does that mean. So the operation would be accumulate. So the sum A, accumulator A, and then there is A, and then X and Y. X is also matrix, Y is also matrix, and then Y is the transpose. Okay, so you are using the transpose. Okay, so for 32-bit data, so how do you represent it, and then how it works, or what instruction that you use depends on what data that you are using. For example, if you use 32-bit data, then X and Y both are 4 times 1 array of elements. Okay, so there is only 1 row and 4 columns. Okay, just the vertical, one column. Okay, for 16-bit data, then you have 4 times 2 array of elements. So 4 rows and 2 columns. For 8-bit data, 4 rows and 4 columns. For 4-bit data, 4 rows and 8 columns. Okay, that's how you represent. So this way, when you do this way, X and YT, the X and the Y, the transpose of this is always going to be up 4x4 set compatible with accumulator, because whatever computation that you do here, whatever representation that you do, or whatever input that you do, the give has to follow the specification that is defined as an accumulator, right? So the whole goal is to, you have input data. Let's suppose you want to multiply these two matrices. If you want to multiply these two matrices, then when you give the input to the accumulator, then accumulator has to support that multiplication. To support that multiplication, you have to look into what is the accumulator feature that is available in the architecture, and then you have to make your input that is particularly specific to that accumulator so that it can process that. Okay, so here the instruction, if you say XBF32ZER, that's how you represent. Then A will be 4x4. It's floating point. So because we have XBF, and then you have X 4 times 1, Y transpose 1 times 4, because X and Y are same, just a single column. So when you transpose, you go into one row, right? So one, and then you have a number of matrix additions that you do per instruction is 16, because it's 4x4. Now XBF 16-bit data 0-2. Then you have 4x4, 4x2, 2x4, and 32 additions that you do, and so on. If you go into 4-bit data, then it's 4x4, and then you will do 128, 128 additions. Okay, so that's how it is provided there. Okay, I have to just a second. Okay. So let me go to next one here. Okay, so accumulators are 4x2 arrays. So this is the extension that I was talking about. So far we talked about 32-bit data. In 32-bit data, the accumulators are 4x4, because one BSR, the vector scalar register, is of size 128 bits, and then you could accommodate in a row 4 values or the elements. But here, since the extension is going to 64-bit, then in a row you can only store 2 elements. So that's why the accumulator for 64-bit is going to look like this. Okay, so 4 rows and 2 columns. And then here again, you have to now, if you have a 64-bit data, then you have to make sure that this accumulator can handle whatever input that you give, and then you will do the change based on the input that supports this one. Okay, so for this one, you can extend like this. So you have input 1 accumulator and 3 VSRs, X1, X2, Y, and output would be 1 accumulator. Operation is going to be A. So you write in A the matrix A plus X1, X2, and then transpose of Y. Okay, so when you do X1, Y2, and Y, these are 2 times 1 array of elements. And then when you make this X1, X2, and then transpose of Y, then it is always giving you 4x2 set. Okay, so here the goal is to accommodate any data to this accumulator, the resulting matrix from the computation. So in the previous one, if you have one column of 4x1 and then 1 row of 1x4, then you will get the 4x4, and then it was helping, it was fitting the size of accumulator. Here the output has to be 4x2, and then so for the output to be 4x2, you have to do the computation in such a way that the output is going to be 4x2. So in the operation, A is 4x2, so there is no problem. So you can assign to A plus, and then when you do X1, X3, and Y transpose, then this is going to give you the result that is 4x2, and then you can put in the accumulator. Okay, so the instruction is going to be XBF. Now you have 64 and jar. So A is going to be 4x2, X is going to be 4x1, Y is going to be 1/2, and then X1, X2 are 4x1. And then when you do all this, then you have number of matrix additions per instruction is going to be 8, and then it fits that accumulator. Okay, so now we have load pressure and unit latency. So these are the 32-bit results here. As we mentioned before, for the 32-bit results, you can support 8 accumulators. So that is 8 by 16 results. Okay. And then there are some specific details here. If you look into the figure there, accumulator 0, accumulator 1, 2, 3, 4, 5, 6, 7, you can represent like that. Okay, and then x1, x0, y0, y1, y2, y3, you can do that. So this is how you represent. So here, all the vector scalar registers that you have, the 32 vector scalar registers, using that you are representing these 8 accumulators, and then you can organize like this. You can have that result. Okay, so these 8 accumulators, if you use, they will give 8 times 16 results. Okay, so why 8 times 16 results? If you look into the row, then you will have 8 rows, and then if you look into the column, you will have 16 columns. So that's why this is 8 times 16. Okay. And then if you have 4, so if you use 4 accumulators, then you get the 8 times 8 result. Okay, just 4 accumulators you are using, not 8 accumulators total. If you use 2 accumulators, you will get 8 times 4 results. If you use 1 accumulator, then you will get 4 times 4 results. So depending on your need, how many accumulators that you want to use in the matrix multiplication. Okay, so depending on whether you want to use all the accumulators, because in total there are 8 accumulators available. So you have the choice to use all 8 or 4 or 2 or just a single one. And then you see some how many instructions that you could support, and then what is the VSR load and all that. Okay. And then if you use 8 accumulators, then they tolerate the most latency. Okay. And then so if you use 4 accumulators, then they work well in the simultaneous multi-threading nodes, and then so on and on. So they have specific properties that you could, you could see to make decision on in this particular system, whether I want to use 8 accumulators or 4 or 2, or I will just want to use 1 and then build on that. So this is what the outer product looks like here. If you look into the red one is m times n matrix. So this plus equal to we are doing. So basically what you do is that you do the computation on the right side, and then that computation is stored in m times n matrix by adding whatever in m times n. Okay, so on the right side, let's suppose you have two two matrices, m times k and then n times k. Okay, so let's suppose this is what is happening. And then, so how do you do the outer product? So for outer product, this is how you do the outer product. So if you look into the first column on the horizontal matrix, and so there is horizontal and vertical. Okay, so the first row, first column of horizontal, first row of vertical. Okay, and then so you multiply that, and then you get one number, or one one matrix, m times n. Okay, similarly, second column, second row, m times n, the orange one. Okay, similarly, you go continue that way, and then you go, let's suppose, into yellow one, m times n, right? So when you do that, so every computation m times n, the outer product is going to be m times n array. Okay, and then you have this pluses there. So m times n, you get the one, and you sum with the other one, you sum with the other one, you sum with the other one, and then when you do total, then you will put in m times n. That's how it works. So load is small. So how does it work? The microkernel. Why do we call it a microkernel? Because at the bottom level, that's how the computation is done. Okay, so in the matrix multiplication, the matrix may be very, very big, but when you go and then write the function on how do you multiply, then at the bottom level, this is how it works. So, and then the computation cannot go further below than this. Okay, this is the last level where you do the computation. So you load a small squarish panel of C, so m times n, right? And keep it in registers. So you load it, and then you keep it in register. Okay, so for the matrix multiplication, so you do this squares of C and then keep in registers, and then you will load one small column of A, one small row of B. Okay, so this this matrix that I have shown on the right side may be a subset of the big matrix, right? So you load one small column of A, one small row of B, and then apply the outer product operation, and then accumulate the results, and then repeat the process. That's how the matrix multiplication is done. So instead of just looking into one and one numbers, one element and other element, and then do the multiplication and everything, you use a little bit more functional approach, a little bit more data, more smaller metrics, and then so you have this computation happening, and then it helps to minimize the number of operations that you do. Okay, so what is a GEMM? So that is general matrix multiply. Okay, so it's very very basic way to do the matrix multiplication. So if you look at BLAST is also one benchmark that deals with this matrix multiplication, and then they run against a BLAST and then LinPack and everything. So this is how the computation is done using accumulators. And then this is one example of how do you write microkernel using 8x8 virtual accumulator. Okay, so we said that the accumulator is a shadow because it resides inside the vector scalar registers. So here, this shows how do you write one. So if you look into this one, this is 8x8 virtual accumulator you are using. So here, let's suppose the first one is, here, first you have to load the accumulators. So you have, let's suppose you have matrices, right? And then you want to multiply those matrices. So to multiply those matrices, what you need to do is, first you have to load the accumulators. So you have 8 accumulators, and then you can load them, right? So you load the accumulators. After you load the accumulators, then you have to transfer to the accumulator. Okay. So you have to transfer the data so that it works as an accumulator. After you transfer the data and it works as an accumulator, then you have to compute. When you compute here, depending on the data, you have 96 compute elements. So 96 compute elements is you are computing one 4x4 matrix, another 4x4, another 4x4, another 4x4, another 4x4. It has to just go on and on up to you reach to 96. So here, as we have seen before, how much computation that you do. For example, here this is m by k and then n by k. And then if you look into this one, then how many computations that you do. Here, this pluses that you see. So you have to do all these computations and add to this m by n. Okay. So this is just one example. So here, compute 1, compute 2, compute 96. After you computed the 96 with adjustment on the parameters and everything, then you have to transfer data from the accumulator to the vector scalar registers. And then after that, you store accumulators. So when you say store accumulators, then you are storing the computation that you've done using the accumulator approach to the vector scalar registers. Okay, so here LXP is going to be load the register, right? Load the register, and then here, how are you loading? So since you are working with 32-bit, so you have 0, 32, 64, 96. Again, you go into 4, that is 16, 48, so on. Okay. So here, this way, you could load the accumulators. You can transfer to the accumulator from these registers, the vector scalar registers, and then you go into computation. You do the compute, and then you have to do the computation, repeat the computation for all the elements there, all the rows and columns there. So you have to do the computation, and then you transfer that computation from the accumulator to the registers, and then you store that information to wherever you need to store. So this is the microkernel implementation that you could do. So here, so the XVF 32 JER that we studied. So PP has some additional feature. I forgot here what does it mean by that. Let me just see whether I get that information. Okay, so what is the number that you are using? For example, this 8 or 16 or 32, whatever you use. So that goes after, uh, information there. So this PP 32, maybe it says precision or I will answer that tomorrow. Okay, so right. Okay. Yeah, instruction mnemonic. Yeah. So so that's how you use this data. Okay. So this is how you could implement a microkernel. Using virtual accumulator. This is virtual, so you have to you have to specify how you want to use this accumulator feature, because that accumulator feature itself is not given separately. You have to use the vector scalar registers to support that accumulator feature. So that's why I think that's why it's optional feature that you could build on top of the vector scalar registers. So all right, so the conclusion is that there is a number crunching feature. Okay, so matrix multiply assist instructions are there, and then also you can have the SIMD. So the SIMD one, right? Single instruction, multiple data. So basically here what happens is that if you execute one instruction, that instruction will not just work on one element or the corresponding indexes, it will work on certain number of indexes. Okay, so that is how the SIMD works. So that's why single instruction, multiple data. So for multiple data, particularly if you want to add two arrays or two matrices, then if you apply, if you say that, okay, add, this index, add A and B, two matrices, then it will go on applying that instruction to certain number of indices, and then the data will be added just at the same time. So that's the same computation. Memory bandwidth, so open memory interface. So there is an open memory interface. We'll talk tomorrow when I talk about Power 10. You will see what are they doing related to memory bandwidth. Also about interconnect, you are going to see what are they doing about making, accessing the elements, reducing the latency there. So so there is a open CAPI. The Professor Hopsty would talk about open CAPI a little bit more. I will not touch that, but what we see is that the Power 10, what is the feature that is available there? For example, how do they interconnect? How do they communicate? How do they cluster and everything? I will talk a little bit about that when we talk about Power 10 processor chip tomorrow. So this matrix multiply assist instructions provide a new level of performance for dense linear algebra and related computations. Okay, so you could see that you could exploit those features to expedite the computation. We did not talk about how much benefit the accumulator based computation gives for matrix multiplication compared to individual individual computation. But there are results that they show that it does way better. Okay. So open memory interface provides a new level of memory bandwidth for computing systems. So you will see there is huge capacity, and then it is more versatile. We'll see tomorrow when we talk about Power 10. We will see some of the details on this one too. So you could see that from this accumulator, you could see that actually using that architecture, using the resource, the registers that are available in the architecture itself, you could build something on top of that, exploiting those registers. How do you manipulate them, right? So MMA, the matrix multiply assist. somehow uses the accumulator concept that was designed, and then the accumulator is a shadow. It's nothing, nothing like the not the new registers are assigned to it. Everything existing registers, you exploit them in a certain way, and then you try to do the computation based on those registers, and then you have these functions. These functions will tell whether this combination of registers you use them as an accumulator or use them individually as vector scalar registers. Okay, so from that you see that there is a room for growth. You can build on top of that. You can put more custom features, and then so that's why this MMA is an optional feature. You can use it, or you do not use it. You can enable or disable this feature. So the open power system itself is trying to see how to put this there's fundamental instructions that are needed to exploit or expedite the process of number crunching faster by building these instructions itself that can exploit the architecture. All right, with this, I think I want to stop here today. Today we have somehow 9 minutes time, 8-9 minutes time. If you have anything related to this lecture, maybe I will answer, and then tomorrow we'll start with Power 10.
Yes, so Professor, I'm not sure whether it is relevant, but how does the RISC-V versus powered open power architecture, what are the major differences that you look into? Or they are a kind of a parallel platforms with similar capabilities?
That's a very good question, Dr. Gajar. So this initiative of open power is it started with some companies, and then IBM and everything, and then there is another set of researchers, and then the group, and then RISC-V is almost parallel kind of initiative that is going on.
Yeah.
And then there are some differences on how do you manipulate registers, differences on base set architecture, some differences on compliancy, all that. But if you look from the bird's eye view, they look very similar.
Okay.
Very similar. My understanding is that in RISC-V, I think there are less number of instructions, or somehow little bit more constraint. But if you want to see, okay, which one is outperforming, is there one outperforms another or something? It's hard to tell.
Yes, I fully agree to that, because IBM and open power more of a kind of a high performance computing point of view, whereas RISC-V they are looking at with a general purpose to look from the lower bottom to the higher one. One
Right.
another question I have is regarding the people are talking a lot about the AI and ML. So what are the kind of similar to the MMA kind of architectural features that people are working or research is going on to have architectural hardware feature added within the processor? Yeah, Dr. Das, you also were interested in saying something. Yeah, please continue.
No, I mean, my answer was to the previous question. Actually, I can give you a software developer's viewpoint, how we have found power architecture different from other RISC-V architecture. So in power architecture, what we have found, they are exploiting the parallelism in a much better and in a much scalable way. For example, like they have introduced like the 8 simultaneous multi-threading, which is totally new in this field. I have never used it in any other machines. And number 2, possibly there are some more instruction level parallelism in the hardware level. I am not sure about it. The other thing that was significant to our performance gain in big data analytics was they were using 16 DIMM channel. because of which actually the data transfer rate between the memory and CPU was significantly high for big data analytics. So that those two key things actually made a lot of difference in our application. So this is just a software developer's view, not too much onto the architecture perspective, maybe.
I think if you look from very base architecture, okay, these are the advanced features that we use for parallel computation, use for SPC and everything, and then that's why I think PowerPCs are used as the computing nodes in the supercomputers and everything in that. But if you look at the base architecture, for example, what are the differences on the computation model? What are the differences on the instructions? What are differences on how do you add two numbers, right? So if you look into the base doesn't differ that much. I think just the differences on whether you are using load store kind of architecture or memory based architecture. For example, you can go and directly access memory and then do the computation too. So if you talk about load store architecture, then whatever architecture that you use, you have to first load the data from memory to registers and then do the computation and then write back to that one. So when you look from the fundamental point of view, not much of a difference based on the instructions available. But when you go to the higher features, for example, whether you support parallelism and everything, yes, it goes and then makes a difference. I would like to go back to answer what are they doing about AI and everything. Tomorrow, when we talk about Power 10, we'll get to see a little bit more into the features, although we cannot go into detail. Like, for example, today, matrix multiplication, we talked about the accumulators and then how things work. I'm afraid that I cannot go that detail tomorrow because there is a lot to cover. But yes, what I can say is that they are working on that. For example, someone uses Power 10 processor to mine the cryptocurrencies. Mm-hmm. Then what are the security features that you need? What are the like, for example, can you make the system run the SHA 256 and everything? This encryption mechanisms they run. Can you run faster? What are the constructs that you make sure that they are in the system to support that kind of computation faster, right? So they are working on that too. So they are providing the power in the system itself so that you could run those computations faster. We have to take their word, otherwise we have to go and then see what in fact they have done, or we trust them. We believe them.
Okay. Thank you. Yeah. Thank you so much.
But those features are there. They are working on the memory bandwidth. They are working on interconnection, so that when you make a supercomputer, then you do not have these bottleneck points. We want to remove these bottleneck points, right? And then for that one, you have to run this supercomputing load to see how many bottleneck points are there. I mean, if we run our normal load, you have a PowerPC, and then if we do our everyday work, we do not see those bottlenecks. And then we say like, oh, this system is fine.
Okay, thank you so much. So with this, we come to the end for today's session. It was, in the true sense, very informative about the Power IC architecture and the detailing, and specifically, as you explained about the architectural and the software ISA of the MMA, great thing and good for the high performance computing. Thank you so much. Wishing you both a great day ahead and good night to all the students.
Yeah. See you tomorrow. Good night.
Yeah. See you tomorrow. 7 o'clock. Your session will be from 7 to 9, and then Dr. Peter Hobbsy will take from 9 p.m. onwards.
Right. I'm afraid that I cannot cover all the material that I promised.
No, this is going at a right pace, and this is all good, sir.
Right, but I don't want to just toss the topic and then just move from that topic. I want to talk a little bit about it. So, but what I promise is that even if I'm not able to finish what I promised in the in the topic list there, what I do is that I'm I will make sure that I will share the slides and document with
Great.
the students so that they can go and read themselves and then get to know better.
Okay. Okay. Yeah. Thank you.
And maybe
All
we
right.
can share both the slides. I mean, all the slides we will accumulate together and we will send it to Dr. Gajar Gokarna.
Yeah. Sure. Sure.
No, no.
Sure.
Yeah,
So
that's what
we
we
have
can
to share project files. I will share
Yeah,
those.
exactly.
We will share all the presentation slides that we used in your lecture and then my lecture.
Mhm.
And then for example, loop unrolling, if I'm not able to cover, I will make sure that I will share those slides.
Sure.
And then we'll also share project description so
Yeah.
that
Project description, if you can share by tomorrow, that will be great. Maybe in a PDF format, so I can pass it on to the students so they can.
I will send you today the
Yeah.
project description and then the project files. So they have to come together.
Right.
There is a question, I think, from some student. Any
Yeah.
research area or technique?
To check and test the inbuilt hidden instructions in our product as security perspective. What do you mean by hidden instructions?
Yeah. Samyak, you can turn on your mic and ask. Yeah.
Oh,
So
they are not.
what my main is like they are not defined in a ISA, but some company or maybe some group of people have added some extra instruction in their product to be as a security breach or maybe used in a such a way or as a data breach.
So this is what happens. So there is if there is a custom extension that they are doing, then if they do not notify IBM that, okay, we are developing this one, it is working, and then we want it to be adapted to the architecture, then we will not know what is going on. Okay. So for example, if you develop something new that is not there, and then you want to be included in the architecture, then you have to write a proposal to do that. Okay. It's like research, right? When you do research, you don't know what is happening. You know the state of the art, and then probably you build something, and then sometimes there might be overlap too. But if you stay in the mailing list of Open Power Foundation and then the IBM, the blog and everything, and then what the lab is doing and everything, you get to know what is the state of the art on the development in the instruction set architecture and also on the custom features they are trying to build.
Okay. Thank you. Wishing you all a great day and night ahead.
Yeah. So see you tomorrow. Bye.
Bye.